All right, I think we're going to get started. Welcome to tonight's Alumni Speaker Series events, The Golden Ratio, History, Myths, and Uses in Nanotechnology with Jacob Trevino, SU's class of 2002. To introduce Jacob, we welcome Megan McMullen-Blue, who is also a member of SU's class of 2002. Megan was a communications PR major. She is the Director of Development at White Plains Hospital and President of SU's Alumni Board. We also welcome SU faculty and staff attending tonight's event. President Jonathan Green and First Lady Lynn Buck, Vice President for Advancement Melissa Kimura, and Associate Director of Alumni Relations Susan Kreischer. And I am Becky Dietrich. If you have questions for Jacob, please use the Q&A feature to submit your question, and we will do our best to answer them at the end of the session. I'll turn it over to you, Megan.
All right, perfect. Well, welcome everyone, and thank you for joining us. I know you are in for a terrific evening tonight, and I look forward to introducing my fellow classmate, Jacob. So Jacob and I both graduated the same year. I always knew him as a very good runner, and immediately prior to this conversation, he shared that he's lost count of the number of marathons he's run. We think it's 4, but either way, all these years later, he is still incredibly impressive, and I'm very excited for you to hear from him tonight. So I will share a little bit from his formal background in case you weren't able to grab that when you registered for the event. But he is a nanofabrication facility director at the New York University and a principal scientist at Chemeleon, a Brooklyn-based startup company, which seeks to apply nanotechnology, photonics, and molecular recognition to create novel devices for the commercial, medical, environment, and food industries. Jacob is also an adjunct professor at Columbia University in its Department of Electrical Engineering and a founder of Nanotech Alliance, a digital platform that fosters growth of the nanotechnology community in the greater New York City area. So I certainly feel like an underachiever. I know you're going to be wowed by Jacob, and I look forward to you hearing from him. So I'll turn it over to Jacob.
Thank you, Megan, and thank you, Becky, for the introduction. I'm excited to be here. This is a really fun opportunity to get to speak to some of the old alumni. I know some people who have signed on, Mike Latonin, I know you're on there, an even better runner who I miss dearly. So let's just jump right in. Let me share my screen. Second here. Let's go full screen. Can you see it full screen, Megan? All right, great. Okay, so golden ratio, history, myths, and uses in nanotechnology. So I'm going to first, I should have put into the title Fibonacci sequence as well, because you can't talk about the history of the golden ratio without talking about the Fibonacci sequence. And if you've never heard of that, don't be scared. I'm going to walk you through this. And so let me give you a quick little outline here. So we're going to start with Fibonacci. It was actually a person back in the 1500s, and talk about his contributions to mathematics, his sequence, and then how the golden ratio sort of blends into the Fibonacci sequence. And then we're going to talk a lot about, really briefly, a bunch of different fun applications and myths and truths and places where you find it in nature and in engineering. And then we're going to switch gears halfway through and jump into my area of specialty, which is nanophotonics. And again, if you've never heard that word before, it's okay. I'm going to walk you through it. And we'll then sort of mix it all together and show how I can use the golden ratio and the Fibonacci sequence to do some really cool things in nanotechnology and nanophotonics in particular. So it starts with Fibonacci. Everyone knows him as Fibonacci, but his actual name is Leonardo Bonacci. And so Fibonacci comes from Phyllis Bonacci, which translates son of Bonacci, which means son of Bonacci. What he's really famous for, even what he should be known for more than just his sequence, is the fact that he wrote this seminal work called Liber Abaci, otherwise known as the Book of Calculations, where he introduced the Western world to Hindu numerals, which is a really big deal, considering before that it was Roman numerals. Roman numerals are very difficult to do things like math with, right? Simple as adding, figuring out your taxes back then, or being at the market and trying to calculate how much you owe someone. And so the Hindu Arabic numbers or figures are what we know today as 9, 8, 7, 6, 5, 4, 3, 2, and 1. And he also introduced the sign 0, which also known as Zephyr. And with all these numbers, now we can pretty much write any number that you can possibly think of. And this holds massive amounts of power, and he really deserves a lot of credit for this achievement. I don't know where we'd be if we'd be many years behind if he hadn't done this. And so in his book, he introduces the numbers up front, and then he goes through and gives a couple different examples in, like I mentioned before, commerce and currency measurements, and how it could be used. In another section, he actually starts talking about different kinds of situations where you can use these numbers, their true power, in the way that you couldn't do before with, say, Roman numerals. And in one example he gives, he talks about how can we describe the growth in the number or the population of rabbits over the course of, say, a year. And this will make more sense in just a minute, and that's what we're going to talk about, because from that comes his famous Fibonacci sequence. He also then goes into talk about irrational numbers, which is, in this one book, is just a massive amount of really important milestones for mathematics in general. So he deserves a lot of credit for this work. So the rabbit problem, like any good scientist or mathematician, he sort of comes up with a thought experiment. Like Einstein used to do lots of thought experiments. You sort of set of rules for this somewhat realistic sort of idealized situation, so that you can sort of run through this in your head and make sure that it makes logical sense, and you can prove out a certain way of thinking, in this case, a certain sequence. And so the rules are, there's 2 rabbits to start with, right? There's a male and a female, and they, at the age of 1 month, they're able to mate and produce offspring, 2 bunnies, actually. It takes a month for that pregnancy to take course. In this situation, at least in the context of the time frame we're talking about, these rabbits never die. And the mating pair always produce another pair that's a male and a female. Okay, so the question then becomes, okay, after so many generations of this cycle, how many rabbits are we left with? And so let's do this. Let's do just a couple iterations. So month 1, we start with 2 slightly unbelievably fictional adult rabbits, male and female, that mate. And then in a month, they give birth to a male and a female bunny. And so now we've got the 2 adults and the two bunnies. In the next month, those 2 bunnies are now old enough to mate, and in this next iteration, and there's 2 new bunnies as well. And so this carries on. You keep going, and you keep getting more and more rabbits, and you sort of, it's not quite exponential, but it grows. And so this can go on and on and on as long as you want it to go. But where the Fibonacci sequence comes in is when you actually like break it down and sort of do some number keeping. And this will become more interesting as we go. But let's do it again. We have 2 adult rabbits. We're going to call a pair of adults A. And then we have no babies yet. That would be B. And in total, there are 2 pairs right now. In the next month, you have, again, the 2 new ones that are now present, and those are represented as B, as a pair of babies. And so you have 1 adult, 1 baby, 2 pairs. And this carries on. You can keep doing your numbered keeping. And what ends up coming of this, it looks kind of abstract, but if you look down the pairs of adults, you start seeing a sequence of numbers being generated. It starts with 1, then the next sequence is 1, 2, 3, 5. And if you want another one, it would be 8, and another one, it would be 13, and so on. And you also see that pattern sort of is shifted here as well. So there's 1, 1, 2, 3, and it would be 5 and 8 and so on. And 1, 2, 3, 5, 8, and so on. Right. And so this sequence is prevalent in all these different scenarios. And this is actually known as the Fibonacci sequence, and it can go on indefinitely. And so there it is in all of its glory, right? And you can actually, you don't need that little thought exercise. You can just do the simple equation to figure out what the next number should be. You just take the two numbers and you add them together to get the next one. So 1 + 1 = 2, and 1 + 2 = 3, and 2 + 3 = 5, and so on. And this carries on, again, indefinitely. And at this point, you're like, cool story, bro. Why do we care? What does it matter? What is this useful for? And so let me, we're going to give you a couple different examples of how this can be used. But what's going to be more important is how it relates to the golden ratio. This sort of important ratio, this number, this irrational number, and that'll then come through later on when I show you how I actually used it and why the Fibonacci sequence comes into play. But looking at the Fibonacci sequence on its own, a fun little trick you can do is if you ever need to convert miles to kilometers. Say, for example, I want to convert 5 miles to kilometers. Well, you go and you find the 5 in the sequence, and you go over 1, and you get pretty close estimate to the 2 kilometers. It's off by just a few decimal points. Say I want to convert 34 into miles, into kilometers, 34, go over 1, 55. So it's really close. So it's a nice little, if you can do a very quick, you can generate Fibonacci numbers in your head pretty easily by just adding the numbers until you get to where you need to be. And you can keep doing this indefinitely. And the first time I saw it, I thought this was pretty interesting. And I didn't understand why the Fibonacci sequence could possibly do this. And we're going to come back to this. So it has to do with that ratio again that we're talking about, the golden ratio. So put a pin in this, how we did this little conversion, and it'll make more sense in a little bit. So here's a fun example of how the Fibonacci sequence comes into real life. And let's look at honeybees. And we're going to look at sort of the genealogy of a family, of a honeybee family, or the family tree. And in the honeybee's hive, or there's always a queen bee, everyone knows. There's worker bees, which are female, and then there's drone bees, which are male. And interesting enough, not all bees have 2 parents. It's kind of unique to bees in this way, that male bees are produced from the queen's unfertilized eggs. So that means that a male only had a mother and does not have a father. That's always the case. The female, on the other hand, is produced when the queen is mated with a male. And so the bees have a mother, and the female bee has a mother and a father. So the family tree has this weird dynamic where if there's a male, he only had a mother and no father. If it's a female, then the female had both sets of parents. And so when we look at let's start with the queen bee, or we start with a drone, right? The drone had a mother, but it didn't have a father, right? Because as we said, males don't have fathers. And then that female had a mother and a father. And then we can continue on down this path where female, mother, father, male, no. Mother, father, just a mother, or mother, father. And so this carries on and goes on for a long time, right? As far as you want to go. And the cool thing is with each generation now, what you can do is you can look at the number of bees, for example, in each generation. And lo and behold, we see our fun Fibonacci numbers popping out: 1, 1, 2, 3, 5, 8, 13. And beyond that, the number of females in each generation is 1, 1, 2, 3, and 5. And so just an interesting place where the Fibonacci sequence actually shows up in real life. There's lots of other scenarios as well. We're not going to talk about those. We're going to talk about using the Fibonacci numbers now in something you may have seen before. And as we go, you'll see more and more of these things that you'll recognize in real life. So we have the Fibonacci numbers. The Fibonacci sequence starts with 1 and 1, right? And so we're going to draw little boxes, and the box sides are going to be the length of the number, or the value of the number. So in this case, it's a length of 1 and a length of 1, width and height. And we just put these first two together. The next number is 2, and they fit nicely into the length because we did add 1 plus 1. So it makes sense that this side is 2. And we can do the same thing with 3 and 5 and 8 and 13 and 21 And we can keep doing this and adding them up to, and as we add up higher and higher. But what you might have seen this coloration or this image before. What it is a precursor to actually drawing the golden spiral or Fibonacci spiral by inscribing a quarter circle of an arc inside of each one of these little boxes. And you end up creating this neat little spiral, which I know you've seen before, maybe. I think a lot of you might have seen it, especially nowadays in memes and on the History Channel and all their shows of ancient aliens and everything else. But the Fibonacci spiral is a special type of logarithmic spiral. But there are lots of logarithmic spirals. It's not special to Fibonacci. It could be a different kind. And so these things are found in nature a lot of different places, actually. And so this is an example of a nautilus shell, which has a logarithmic spiral in it. That's the Fibonacci spiral overlaid on top. Spiral galaxies have the same patterns as well. They can be modeled this way quite nicely. Weather patterns, you've seen this same shape. And again, one thing to note is that while these all look like they're perfect Fibonacci spirals, it's because they were chosen to be, but they're not specifically Fibonacci based. They're logarithmic spirals. They could be slightly different. And so just to be skeptical, people are always trying to find a place to shove a Fibonacci spiral on top to give it some special meaning. And here's Conan O'Brien, and someone has nicely placed the Fibonacci logarithmic spiral on top of it. People put it everywhere. You wouldn't believe the things you can find on the internet of people just slopping this anywhere, but it usually is not true. So how's the Fibonacci sequence and spiral related to the golden ratio? And what is the golden ratio? Because I haven't told you yet. So let's start with our good friend, the Fibonacci sequence. And what we're going to do is we're going to start dividing one by the next one by the previous one. So 1 by 1 is 1, 2 by 1 is 2, 3 by 2 is 1.5, and so on. And for those of you who are maybe in a technical field or analytical field, you start to see a pattern just by looking at the numbers that are popping up. If you start plotting them, you'll see it more easily with your eyes here. You start converging, and they converge on a very specific number. That number is the golden ratio. We often denote the golden ratio with the Greek letter phi, capital Phi. And this number is irrational. It's highly irrational. I was in the next slide to actually say it, but it is the most irrational of all irrational numbers. And that is actually a thing. Irrational numbers just meaning that it goes on repeating forever, right? Just like pi is, just like the square root of 2 is irrational. But this one is the most irrational. And that, I know that's hard to believe, but just take my word for it. If anyone's interested, I can tell you about it afterwards. But it's this number that pops out of the Fibonacci sequence. And going back to our previous sort of section where I told you how to do conversion using the Fibonacci sequence from miles to kilometers, you see that the actual conversion number is very close to the golden ratio. And so that's why that actually works. It's nothing special. It just happens to be close to the golden ratio. And it just is a nice example of how the Fibonacci sequence is tied to the golden ratio. So in order to see the golden ratio in the real world, we need to look at it in terms of at length. You can look at it in different ways, but the most common way is to make these small sections. And the golden ratio is going to be the ratio between these two sections, A and B. And you can set a rule. You don't have to use the Fibonacci sequence to generate it. You can set a very simple rule. I'm always surprised that this works, but you can create the golden ratio or a golden section by making sure that this rule is met, that A plus B, which is the total length, is to A, as A, the longer one, is to B. And so you can write that as this very simple equation. And anytime you do that, as long as this is true, the ratio will always be exactly the golden ratio. It's kind of strange, but that is the way that it works. And then mathematically, you can actually define it a different way. These are all the same numbers, the exact same numbers. But you can write the golden ratio mathematically 1 plus the square root of 5 over 2, if you ever need to generate it in a computer, for example. And I mentioned this before, this is the most irrational of all irrational numbers. Just a good example of how that's sort of what that means is it's difficult to approximate this number by fractions, in particular in mathematics with continued fractions. But for example, pi, we think of pi as being a very irrational number. It's actually not. If you use 22/7, it approximates pi to a very, very far out number of decimals. The golden ratio, you need very large numbers to approximate it to any kind of accuracy. And so that there's a proof, but it's effectively the most irrational of all irrational numbers. And that makes a difference in what we're doing later. It pops up in random shapes. If you take a regular pentagon, any pentagon, and you pentagons have the same sides on over here and over here. So we set that to 1 and 1. If you draw a line from the base of this one to the top of this one, it will always be the golden ratio if it's a pentagon, or if it's a pentagon. If it's a pentagram, there's even more golden ratios embedded into it. If you take this length to be 1, then this length here of a pentagram will always be the golden ratio. If you take this length here, it's always the golden ratio squared. And if you take this one here, it's the golden ratio cubed. It seems weird that in these basic shapes that you would have this irrational number just sort of embedded into all of them. That doesn't happen very often. The square root of 2 sometimes, but this is a very specific number that happens in geometry and in nature many times. This whole concept of the golden ratio being special has been known for a long time, and Euclid and Pythagoras in ancient Greece knew about it and talked about it. I'll show you later that the Egyptians must have had some concept of it as well. But it wasn't until the early 1500s when Luca Pacioli wrote The Divine Proportion, this book that sort of made it into mainstream media, if you will, at the time. And it was cool because Da Vinci was the person who illustrated the figures in it. And in here, they discussed in great detail the proportions and their applications to geometry, to art, how it's found in nature. They really went in depth. And after this book was published, it became pervasive. People started designing it into buildings, into art. But the really cool thing was that both of these gentlemen gave Fibonacci credit for being the guy who sort of figured out the connection between the Fibonacci sequence and the golden ratio and its importance. And so just a few examples where it's found. This is in art. This is Albert Dürer, my favorite Renaissance artist, German. He was a little bit cocky, given this is a self-portrait of himself made to look like Jesus in many ways. But he built on the golden ratio into many of his paintings. And so this is an equilateral triangle. And if you draw it right, over his shoulders and head, it splits the painting into a perfect golden ratio, the top and the bottom. If you go into more detail, which we won't talk in this talk or spend time on this talk to talk about, there are several other ratios or golden ratios that he built into his face. And in fact, in another talk, I go in more detail about how people try to assign the golden ratio to beauty. And how people have made algorithms that will calculate using golden ratios of a person's face and tell you how beautiful they are based on some scale. There's no real science behind it, but it's just something that's out there. Another cool example, Sandro Botticelli's Birth of Venus, super famous painting. These lines are just drawn sort of to demark the horizon between the ocean and the sky, and the start of the shell and the bottom of the painting. The painting itself is a perfect golden ratio. The sections of the sky to the ocean is a golden ratio. The sections of the shell to the rest of the painting is a golden ratio. So people knew about this and they built it in, and they thought it had some meaning either to them or just they just thought it was beautiful. It just made a beautiful painting. And it's in many others as well. Architecture, you'll find it going back to the ancients to modern day. The cathedral, the Notre Dame Cathedral in France has the golden ratio built all over it. And so these sort of demark the different sections that you can take and get exactly the golden ratio. Here in New York City, where I am, the UN building also has it built in inherently into many of the sections that they have. The CN Tower in Toronto, most impressively, though, as I mentioned before, is the Egyptians had to have some concept of the golden ratio, because there's a special triangle called the Kepler triangle. And this is where you have the base of your triangle being, unit 1, and the hypotenuse being phi, the golden ratio, and the height being the square root of phi. And so the Great Pyramid of Giza is varies by less than 0.025% from that of a perfect golden triangle pyramid, which is amazing. I mean, the thing is 480 feet tall and off by just an inch or two. And so there's no way that that's by chance. They must have known that, what the golden ratio was, and had some importance to them as well. If you look at a bird's eye view of all 3 of the Great Pyramids, and look at the distance between them and the spacings in different areas, there are many. You can see here. I don't know if you can see my arrow. Can you see my mouse? Okay, good. You can see that the ratios are very close with incredible accuracy, given the distances that we're talking about here between these pyramids. And so if you're watching the History Channel, immediately you think this had to be aliens. I'm not going to say one way or the other, but they clearly knew about it, and they clearly assigned some value to the ratio. In many places, it's called the God ratio or the God number. I didn't go into it in this talk, but it's also found in many different portions of your body, have the golden ratio built in your face, in your bones. It's in trees. It's in, I'll show you some plants as well here in a minute. So it's pervasive. So I can see why people assign some extraordinary meaning to it. But the question is, okay, I'm a nanotechnologist. How does this relate to me and what I do? And so in particular, I'm applying it within a subset of my expertise called nanophotonics. And so anytime I tell anyone, I work in nanophotonics, I usually get a Chris Hart look, and have to explain what nanophotonics is, which is fine. Let's break it down. We'll split it in half. We'll talk about nano first, right? And I think some of you may have heard of nano, but maybe not. So let's talk about it. Basically, it's small. It's very, very small. Nano is it's a unit prefix, meaning 1 billion. So if we're talking about meters, which you typically are when we're talking about nanoscale, you have 1 meter. And so a nanometer would be a billionth of a meter. And we typically denote that with nm here for nanometers. And it's impossible to, if you can visualize what a billionth of a meter is, that's great. I definitely couldn't the first time I heard about it. So let me try to give you some sort of range of reference to know what we're talking about. So on this graph down here, we start with a tennis ball and we get smaller and smaller things that we sort of know about. And on the bottom, these are nanometers, and on the top, these are just meters. And so the space that nanometers sort of is, and where nanotechnology lives, is in this realm of 1 to say 1,000 nanometers. So things like a blood cell are massive compared to the objects that we're making. In everything I'm talking about today, the objects we're making are orders of magnitude smaller than a human red blood cell. We're typically living in this space right here between 10 and 100 nanometers. And the cool thing is with nanotechnology, we can make these structures out of pretty much whatever material we want, and we can place them with nanometer scale accuracy on a surface, arranged in whatever pattern that we would like. Another fun example of scale, just to give you an idea, is this is a scanning electron micrograph by our friends at Sandia National Labs. They love putting bugs on these devices, and I love it. This is a micro scale device that you see. So these are little gears. These are moving components. This is a comb finger drive, and it doesn't matter, but effectively what you're looking at, this spider mite here is about 2.5 times the width of one of your hairs, right? He's tiny. So you could fit 2 of these side by side in the diameter of one of your hairs. These objects that it's standing on are 1,000 times larger than the objects that we make in nanotechnology. So effectively, I should have used it, but you can write your name. We have done this before. You can write your name on an object smaller than the width of one of these hairs on the spider mite. So small, very, very, very small. and that's nano. On the other side, it's photonics. And photonics has two components. It has photon, which, if you're not aware of, photon denotes the fundamental unit of light. If anyone's in physics, it has, wave particle duality. It can be both. It's both a wave and a particle. But in the context of this talk, we're just talking about it as a wave. That's what most people know it as, having a wavelength of light. There's also X at the end, which denotes electronics. Again, in the context of this talk, we're not going to really talk about electronics and electrons, but they do play an important role in nanophotonics. So when we talk about photonics in general, we're talking about either generating light, transmitting light, modulating it, amplifying it, storing it, detecting it, anything that has to do with light and how we manipulate it effectively. And when we're in nanometer scale, we're usually talking about things in the visible wavelength spectrum. So this is light that we can see with our eyes. And if you actually plot the different colors of the spectrum, when we talk about wavelength, it's actually a length of the wave. And you can see that the scale here is 665 nanometers down to, for violet, 400 nanometers. And again, the objects that we're making are routinely half to a quarter the size of this one wavelength. So that's what allows us to do really unique things with nanotechnology. Is when light sees these small objects, it behaves differently. And we take advantage of a lot of these sort of unique interactions. So, and that's all this graph says, is that effectively, or this definition by the National Academy of Sciences, is that when you're talking about nanophotonics, you're using sub-wavelength scale, so things that are smaller than the light itself. These are artificially made things that we design, and we're making light do what we want it to, and make it do things that it wouldn't normally want to do with these structures. So how's it used? There's two, I sort of categorize it into two big areas. So you can either redirect light or reroute it. So this little picture I have over here that I've drawn is sort of a cross section of, say it's a piece of glass, and we put some gold nanoparticles on it in a certain way. And we want light to come in, and we want it to go this way or this way. We can design these to sort of reroute the light in which way we want to. And so applications might be solar cells, which I'll talk about, LEDs. Those two, I will actually show you what we've done in those. But also things like displays on your phone, your TV, optoelectronics as well. That's a field where you're trying to replace using electrons with photons for computing. So that would mean that your computer would be running off of light instead of electricity. The other thing you might do is you might concentrate or trap light. And that has applications in things like lasers or sensors, also in solar cells, but lots of other things. But we're not going to talk so much about that today, but that's a really other big major field or subfield. Okay, it's going to get a little technical here, but I'm going to try to work us through it. In order for me to discuss how we're using these cool little geometric tricks, I need to teach you about diffraction. And diffraction is just a scattering of light by nanostructured materials in a kind of a special way. So again, I'm drawing you a cross section of, say, a piece of glass with some nanostructures on it. And those nanostructures have dimensions that are, say, 100 nanometers in diameter, and they're spaced anywhere between, say, 2 and 600 nanometers. In the special case of diffraction, these things are going to be periodic in nature, meaning the spacing is going to be the same as you move anywhere on the surface. And this could be in 2 dimensions or 1 dimension. So what we're going to do is we're going to pass light of a particular wavelength, and it's going to be, say, red in this case. That light scatters on the other end, and it scatters in what we call modes. And most of it goes straight through with the 0th order mode. And then you get other modes. There's a first order and a second order and a third order, and so on. They sort of spread out. And if I use the same sort of material and I pass blue light now, they're going to scatter at a slightly different angle. And that has to do with the interaction between the light and the structures. And I could scale these by moving the particles apart or moving them together to move these diffraction lines where I want them to be. And so in 2 dimensions, it would look like this from the top down, like these little dots would be nanoparticles that I would place with certain distance between them. And we would shine light through them like this. And this is actually an experiment showing you what happens. So there's nanostructures on this chip, and there's a laser pointing through it. and the laser gets diffracted along these orders into these very discrete points of light. This is where it gets this is where it gets a little bit crazy. You have to sort of just take my word for it. You can go from this sort of geometric space, this normal periodic array in real space, to what we call the Fourier space. For those who are on the call that are mathematicians, we take a two-dimensional Fourier transfer of this structure to get this one. And you see that it looks just like this, and it does mimic it exactly, actually, and you can predict what this is going to look like. But more importantly, what the Fourier space tells us about something is where these dots are represent how light behaves when it interacts with the material. And so when light hits this and scatters, if I draw a circle of a certain radius, that corresponds to a certain wavelength of light. And these points along this line correspond to a certain polarization of light. So you might have polarization glasses that sort of filter out some of the light, right? Light coming from the sun comes in all different polarizations. The laser has one polarization. So what this is telling me that if this polarization, this one, and this one at a certain wavelength, which is the radius, I'm getting light diffracted in a special case known as the Rayleigh cutoff condition, which is just to say that light comes in and goes straight to the right. Right, this is a special case scenario. Not all of it does, some of it goes in a zeroth order, but a lot of it goes here and turns 90 degrees in a hurry and just propagates along the surface. And just take my word for it. If in this scenario, I put a blue light, it would not hit those points, right? This is a shorter wavelength, it's a shorter radius. So I wouldn't get this effect. So only the red light would do this, not the blue. So let's think of a scenario where I want to make all the light that comes in turn 90 degrees in a hurry. What that would look like in the Fourier space is I would have, instead of having just a dot, I would have a width, like a bigger width of this dot, a big dot, or like just a ring effectively. And I want it populated all the way around this ring with light. And that would mean that for lots of different wavelengths, which is lots of different colors, in lots of different polarizations, I'm taking light and I'm coupling it to the right. You have to understand, in this space that's 30 nanometers tall, that's only maybe 400 atoms thick. And so this will be a very, very thin mirror effectively, but at 90 degrees. So just take this into account. And we're going to come back to this here at the end. It'll make sense because now you're asking, why do we care? And that's a good question. So let me give you a scenario. Solar panels. You have these at SU right now. I believe they were not there when I was there, but I believe we have a solar farm now, which is fantastic. You've all seen these before. They're pretty heavy. They require these metal, struts to hold them up because the silicon itself is actually pretty thick. What if we wanted to make ultra thin solar cells, right? And so if we want to make ultra thin solar cells, you can make them really thin and they would be flexible. And you can think of all the fun applications. For example, like you could make clothes out of solar materials that would charge your phones. You could think of curtains that might be taking in some of the sun and converting it into power that you can use in your house. And there's endless applications. The problem is when you do that, you normally in a regular solar cell, you have lots of time for light to be absorbed because it's passing through this really thick substrate that has, lots of thickness to run through before it falls out and doesn't get absorbed. So you have a certain efficiency associated with this. For a thin film solar cell, I can make it so thin that the light doesn't have much time to be absorbed. It just passes through. And actually, there's a mirror here, so it passes through 2 times, it reflects back. So what you can think of doing is what we've been talking about is let's put some nanostructures on the surface. And let's design them in such a way so that the light comes in and goes in the material. That way it can drive through the material and spend a lot of time throughout the width of the structure of the solar cell and make it much more efficient that way. So that's the concept. And we would want this to be broadband, like large wavelengths and various polarizations as well. So now we get to the actual application where we're talking about golden ratio and nanophotonics, now that we've learned about diffraction. Very quickly, again, here's the golden section following this rule. You can make an angular version of this where you bend it now, and you still apply the same rules to these 2 sections, and you get what's known as the golden angle, right? Because it has a golden ratio built into it by default. And it's an irrational angle. And here we're going to get, this is going to be a little weird, but we're going to just step through it real quick. If I want to create a point pattern, so normally you would have X and Y and you would plot that point on the graph. We're going to use polar coordinates, which is R and a theta. And there's a very simple equation you can use, and I'm not even going to step you through this, but effectively the idea is you plug in, this is just an integer, so you start with 1, n equals 1, and we use this angle that we've just made, the golden angle here, and this is just a constant. And so you put it in there and you get some value that puts you at a point in space with an R and a theta. You put in n equals 2, and it rotates you further and it pushes you further out, and you get another point. N equals 3, it rotates further and it gets further away, and you get another point, right? And so you can keep doing this over and over and over again. And when you do that, n get up to say 1 billion, right? In a computer, you start just generating this pattern. And slowly you'll start seeing the formation of something that I'm sure all of you have seen before. I'm going to fast forward this a little bit because it goes on forever, right? And so at the end, you get to some large structure that looks like this. And this structure is, if I can just go on to the next one, something you've seen before. This is the same pattern that's found on the head of a sunflower seed. This is exactly a golden ratio or golden spiral. You'll find them in cactus heads. You'll find them in all kind pine cones, in everywhere in nature, in the way that trees align themselves from the top down, their branches, they're everywhere. And of course, your initial thought is it's conspiracy, some sort of alien influence, but it's not. This is just the optimal means of packing an object radially, right? So mathematically speaking, this is the optimal way to put these particles, as many of them as you can, in a radial pattern on a surface. So that's why nature has over years found it to be that. So back towards our structure, we have the periodic array, which generates the Fourier space that has these dots. That's not what we want. We want a circle, right? We want it to have some width. And so if you just make it completely random, you can fill some of that space. You fill all the space with intensity, but it's not very concentrated. It's wasted in other places. And then you can get into fancy tiling techniques. This is called a Penrose, and you start populating more dots along the circle, which is what you want. This is called a Danzer. Doesn't matter. But then when you use the golden angle spiral, you get exactly what you want. You get a continuous circle in the Fourier space, and you get it to have some width which corresponds to different wavelengths or different colors of light. And so it's ideal candidate for what we're trying to do with the solar cell. And so we did experiments where we generated different kinds of spirals, and you can show that you can make similar objects, but the golden ratio spiral is the best for what we're trying to do, which is concentrate as much light into one circle. And so you can go and make these structures. These are nanoparticles that I've arranged using, these are actually gold nanoparticles. Each one you see is 100 nanometers wide and only 30 nanometers tall, and it's sitting on a solar cell. We can make them tall, skinny pillars, different shapes like a cone and whatnot, out of different materials. But effectively, as a test scenario, we build them on top of a solar cell. This is a tiny little solar cell. You only cover 25% of the surface area with the nanostructures, just as a proof of concept, right? Doesn't matter about the experimental configuration, but what I want to show you is in a regular solar cell without any patterning on it, you would have 0%, say, enhancement of the current that's generated from a light that's shined on it. With that periodic array, you get 8%, right? Because you do have some points along that circle. But with the golden angle spiral, you can increase the solar cell's efficiency by 31% over a reference cell, right? And that was only covering 25% of the surface area, and covering all of it with this pattern. And so that's one way that you can create a more efficient, thin solar cell. I'll add that this thickness of the active material was 50 nanometers thick. That would be thinner than a sheet of napkin or paper towel. It would be transparent. And the other quick application is the exact same thing, but in reverse. So if you want to couple light in, you can also use the same concept to couple light out. And so think if anyone's familiar with LEDs, everyone talks about how efficient LEDs are, and they are way more efficient. They could actually be orders of magnitude more efficient. Most of the light that's generated in an LED is trapped inside of the cell itself, inside of the material, just because of some other things we don't have time to talk about. But one way to get the light out is to design nanostructures on the surface, just like we did for a solar cell. And this sort of shows like an unpatterned surface LED, and this shows a patterned surface LED. Same material, just with a pattern on top. And you can see you can bring out more light from the actual LED. And so we can play with all kinds of patterns, and of course, we throw in our golden angle spiral, and we make them these beautiful little nanostructures on top of the LED with all these different patterns. And don't worry about the data, but really what you need to care about is you can get 10 times the emission enhancement at a particular wavelength that you design. So we design it to work at 1.54 microns wavelength. That's not visible, that's IR. And that's because this is the wavelength that's used for optical communication. So like the fiber in your house that Verizon or whoever else is bringing, this is the wavelength of light that they use. And so you can do this with solar cells. And then I think I'm gonna stop because I want there to be questions, and I want to make sure I can answer questions. But you can use this for quantum encryption. If someone wants to know about it, I can talk about it. But let me stop there and just put this here for a second, and you can ask me questions. Just so if you want to get in contact with me, and we don't have time to talk about it, you can email me at jacob.trevino@gmail.com. Sorry about that. Or the website as well works as well. So let me stop sharing right now.
There we go. All right. So we do have a couple of questions that were pre-submitted, but I'm going to kick off the first question and just ask if you could tell us all, how did you become interested in the golden ratio and just, what you're pursuing now? Like what sort of first piqued your interest and how did this all begin?
I was always interested in complex media in general, like disordered media, and in looking into ways. So like there's always this massive benefit from disordered media, and there's this other benefit from ordered media, but they both have their faults. And so I was looking for a way to find disorder and order at the same time. And so even beyond the golden angle spiral, like I looked at a bunch of different number theory arrays. There's a whole bunch of them that have this unique ability to be complex and disordered, but with knobs you can turn in a deterministic way. So we call them deterministic aperiodic nanostructures. Yeah, so that was just more of a curiosity and trying to get the best of both worlds.
Okay,
yeah,
love that. All right, so one of our questions was, are there any other cultures or religions who recognize numerical patterns and integrated it into their belief system?
I mean, I think yes, absolutely. I think, and I don't know, you wouldn't say it's based on it, but there's certainly numbers that have meanings for different religions, and sometimes they're the same number, right? So like 3, for example, and everyone knows Christianity for sure with the Holy Trinity, right? And it's most here in the United States very dominant. And then ancient Babylon also had 3 gods, Anu, Baal, and Ea, I think it was. The Egyptians had 3 sun gods to represent the 3 different, like morning, noon, and afternoon. Yeah, so I think it's I think we tend to look for numbers and things, and I'm not sure that those numbers necessarily have the significance. We make them have significance. But that doesn't mean they're any less significant.
So we assign meaning to them in some
we do.
Circumstances. Yeah.
Yeah. You could pick any number and then go through the Bible and find just as many references to that number as you would to almost any other number that might have supposedly more meaning.
Right.
Yeah.
Okay. And what advice would you give for the young people interested in pursuing further education in this area? Tell us what you've learned kind of along the way.
Yeah, no, the nice thing is nanotechnology in particular is so interdisciplinary in nature. So like my background in particular, right? So I was physics and math at Susquehanna. My master's is in electrical engineering. My PhD is in material science engineering. So, but I use literally all of those things on a daily basis for my job. And so, but there are times where I don't know enough chemistry to do what I need to do. So I need to work with a chemist. So I think within any of the disciplines, and even just straight mathematics, as you've seen, there's a lot of math involved. You could work in nanotechnology if you're interested in it. So you definitely specialize in the subject area that you're you feel comfortable with and you feel most excited about, but you can always look for an application within nanotechnology to use it. Yeah.
Okay. Tell us, give us a sense, and maybe this is for me, who's non-mathematician and non-nanotechnologist, but tell us, when you're kind of walking around your everyday life, give us a sense of where you see the application. Certainly you drew in the artists and paintings and things like that, but I'm sure it strikes you in a lot of other ways. So give us a sense of that.
Yeah, I think nanophotonics more broadly, not necessarily Fibonacci and golden angle. I see right now the big things are biosensing and medicine in general, being able to manipulate nanostructures to give us, a lot of the stuff in COVID, right? So COVID sensing, vaccine development use nanotechnology, all the gene sequencing is enabled by nanotechnology. So medical field is the big one. Energy is probably the next biggest. Things like solar cells, batteries, LEDs, everything. Because in nanotechnology, the cool thing is you can manipulate the materials on the nanoscale to give them properties that they couldn't have before. And that property could be lighter and stronger. It could be more conductive. It could be, many things. And so you can really apply it to everything, which is really cool to see. Yeah. But I'd say energy and medicine are the two big ones right now.
Yeah. And when you think about the future of the field, kind of what are you most excited about? When you wake up every day, what are you thinking about? What does the future look like?
I can't not think about how profound the effect of quantum computing is going to be. And quantum computing only happens with nanotechnology, right? So to make a quantum device, it's all nanostructures. The computational power that's going to come with that is going to take our technology, all of our technologies, to another level. And I can't even imagine what that's going to look like. But it's exciting, a little bit scary, but it's exciting.
Exciting. All right. Okay, so we have a question that just came in from Gail, and she says, so the golden ratio exists because nature created it through evolution, trial and error. Is that the right explanation? And that explains why it's so effective. Does that explain why it's so effective?
Yeah. I think the best explanation the best example I can give is like if you look at a tree from the top down, the way that it arranges its branches is exactly that same equation that I wrote. You rotate through by the golden angle, right? But you go down. So like the tree rotates and it moves down. And the reason it does that is because it's trying to optimize. It wants as little overlapping branches as possible, so that sun can get to all the different branches and leaves. And just thinking conceptually, like if you don't use an irrational number, then you end up, if say you use 2 as the angle, then you put one here, you move down, you put one here, but then the next one is underneath that second one, right? And so the more of the irrational the angle is, the more iterations you'll have to not be overlapping. And so it just happens and it just happens that the golden ratio is the most irrational of all irrational numbers. So it happens to be the one that a lot of biological things have sort of settled on over time. So, yeah.
I know I mentioned in your intro that you're also an adjunct faculty member at Columbia University. And so talk to us a little bit about the coursework that you teach and kind of if your students only walk away with one thing, what is that? What does that look like?
So the courses I teach are nano-based. A lot of my expertise is in the two areas: photonics, which is like what we talked about today, but also nanofabrication. So there's a whole sort of subfield of how do we make the nanostructures, and all of that comes from the technologies that were developed from IBM and Intel, making smaller and smaller transistors. We apply it now to do a whole bunch of new things, and so a lot of my classes are teaching them the theory and the hands-on of how we actually go and do that, and nanophotonics as well. I think what I try to instill in my students are that it's very intimidating when you first come to nanotechnology. Like I said, like you have all these different disciplines you have to know, and all these, it's very complex, and quantum mechanics and all kinds of stuff. But the thing that I always try to instill in them is that you're not, anyone can do it. And it's really complicated, but you're already here. You've been accepted to the university. You have the subset, the skill set to do what needs to be done. It's just a matter of, you know, time and effort and a little bit of confidence in yourself, and just come back to me at the end of class and tell me if I was not right, that you could not do it. You can do it. And I've never had anyone come back and tell me that you were wrong. There was no way I could get this. But yeah, no, I really enjoy teaching there. It's the students are great. It's fun.
Okay. So I'll lead at the last question, and this is sort of a take on a question that was pre-submitted as well. But you know, some students who are, let's say, still pursuing their education may be skeptical that math can actually be used in your career. So you're already laughing, but what would you say to those students?
I mean, this comment will mean a lot to, well, Michael Tonin, I think hopefully is still on, as a mathematician. He was a math major with me as well at Susquehanna. We took a class called abstract algebra. And at the time, none of us thought there's nothing in this class that will ever in our lives be used. Like nothing's useful. There's nothing in here at all.
Okay.
I promise you, I went back and had to open those textbooks and actually use the information. Like, and it's in my dissertation. It like is in publications that I've had. And it's amazing how many times that has happened to me. All these classes that I took where now in hindsight, I think I really should have paid attention more or taken better notes in that class that I was very tired in. But I think the cool thing about, I mean, mathematics in general is there are so many scientists in the sort of in chemistry and biology and physics that physics people are usually pretty good, but in chemistry and biology in particular, that they don't have the math strength background. And nowadays, everything is team-based, right? It's all collaboration, and you need people with strong math skills. It's an invaluable skill set to have. So if you're in math, yeah, you can find a use for all the things you're learning, I promise you, at some point, if you go into this field.
Right. I love that. My mom is a retired math teacher, so she could kiss you right now. Well, we are right at 8 o'clock on the dot, and I have to say you did a tremendous job of just making this so interesting and so applicable and accessible. So I really want to thank you for your time. And thank you to everyone who joined the call as well. We are thrilled to have you. And it sounds like this group may also be interested in our next talk, which is scheduled for June 22nd. And it's a catchy title, If You Give a Biologist a Kitchen. So lots of interesting things to think about. And that'll be with Alicia Melnick. So stay tuned for that, also at 7 o'clock. And I also would invite everyone on this call to please come back for homecoming, which will be in person October 22nd through 24th. Jacob, I know, will be there because he's a fellow member of the alumni board with me. And so he will be there. You can have the opportunity to ask him all of your questions, perhaps over a beer at Bots. And Jacob has also graciously offered up his email. Again, jacobtrevino@gmail.com. if you have any follow-up questions from this very thought-provoking talk. So thank you everyone for your time, and thank you, Jacob, for sharing your knowledge with us. It was great.
Thank you. Thank you. Thanks for coming, y'all.